Hello everyone, welcome to today's video on solving systems of equations by graphing. So we're particularly talking about systems of linear equations. We've talked about linear equations a lot this year. We know the word linear means a line. So if we have a linear equation, it's an equation that when graphed will give us a line. And when we have two or more of those linear equations, we have what's called a system of linear equations. So we're going to try to solve a system of linear equations, meaning that we're looking for the x value and the y value that's going to make both of those equations true, right? Because the definition of a solution to a singular equation is the value for x, or the variable that makes the equation true. Here we'll have two variables, two equations. We need the value for both x and y that's going to make the both equations true. And then graphically, this appears as the point where the lines intersect. So this is an example. We have the system of equations y equals negative 3x plus 2 and y equals 2x minus 3. One way of solving this system of equations is to graph both of those linear equations, make them lines, and then the solution is just the point, the x value and the y value, where those lines intersect, because that means it makes both equations true at that point. It's also possible, in addition to having one solution to a linear equation, like we have here when the lines intersect at one point, and that gives us the one solution. It's also possible to have no solutions. So that's going to mean when our lines are parallel, right? Parallel lines never intersect, they never cross, so there is no point in common, thus there is no solution to both equations at the same time, so there's no solution to the system. So that's going to be when there's parallel lines, and as we'll see more, that's going to mean that they have the same slope. Parallel lines have the same slope, but they have different y-intercepts. And then if both equations ultimately give the same line, they could look like they're in different forms. Like we know 2x equals 4 and x equals 2. Those are two equations, but they're the same equation, right? They're going to give the same line. In those situations, we'd say the system has infinitely many solutions. Any point along that line is going to be a solution. All right, so let's take a look at an example. First, they did the hard work for us. They already graphed, which is great. So we're just looking at this graph, and we're asked, what is the solution to the system of equations below? So we have the system y equals 3x minus 4, and y equals negative 1/2 x plus 3. Quickly, we can see they correctly graphed that for us. Here we have negative 4, that's my y-intercept of negative 4, and then I have a slope of 3, which is also equivalent to 3 divided by 1. So I have a rise of 3, a run of 1, a rise of 3, a run of 1. So that's the slope. And then we have the second line is graphed as well. We have a y-intercept of 3 and a slope of negative 1/2. Okay, so the solution to the system is the x and y pair, the point where these two lines intersect. Okay? So take a look at this graph. Where do the two lines intersect? Perfect. This is the point 2, 2. Great, 2, 2. We have an x value of 2 and a y value of 2 right there. So that is the solution to this system of equations. When x equals 2, we get a y value that equals 2. That makes both of those equations true, so it's the only solution to the equation. To see what I'm talking about algebraically, let's check that that's right. For our first equation, we have y equals 3x minus 4. So I'm going to substitute in 2 for y and 2 for x. And when I do that, I get 2 on the left-hand side of the equation. And on the right-hand side, I have 3 times 2, which is 6, minus 4. So 2 equals 2. Thus, the point 2, 2 gives us an x value and a y value that makes this equation true. Okay, and then I can do the exact same thing. I'll do it a little bit faster, but I can do the exact same thing for y equals negative 1/2 x plus 3. I substitute 2 in on both sides of the equation, and I will end up getting 2 equals 2. Awesome. So that's the solution both algebraically, it's going to make both equations true, and graphically, it's where the lines intersect. Awesome. All right, now let's do a second example. This one is going to require some more work for us. We need to solve the system of equations by graphing. Okay, so this is my system. I have y equals negative 5/3 x plus 3, and then y equals 1/3 x minus 3. So those are two different linear equations. And to find the solution to the system, I'm going to graph both of them and see where do they intersect. Okay? All right, so let's start with the first one, y equals negative 5/3 x plus 3. Taking a look at this equation, which is in slope-intercept form, y equals mx plus b, where we know m is the slope and b is the y-intercept. What is the y-intercept of this line? Yeah, the y-intercept is 3. It's in the b spot. So that means I'm going to graph this by first putting a point right here on the point 0, 3. Right, the line is crossing the y-axis at 0, 3 because the y-intercept is 3. And then we have to interpret our slope. Our slope, m, is negative 5/3. So I could put the negative sign in the numerator or in the denominator, but we're going to put it in the numerator for the moment. It could be in either way. Remember that slope is equal to the change in the y values divided by the change in the x values. And the slope can give us like directions here to get another point on the line. So if I have a change in my y value of negative 5, y value is up and down. So since it's negative, it means I'm going to go down 5 units. Change in x is 3. X means right, left. So if I have a positive 3, that means I'm going to go right 3. Thus, from this point that I already plotted, I'm going to go down 1, 2, 3, 4, 5, right 1, 2, 3, and here is a second point along the line. And then I can connect them. Okay, and that's my first line. Ideally, we have a ruler, but best we can do for the moment. Okay, so that's me graphing the first line. Now I have to do the same thing with my second line, and then I'm going to see where the lines intersect. So for my second line, I have y equals 1/3 x minus 3. What is the y-intercept for this equation? What is that b? Negative 3. Got to be careful. We know it's negative 3 because it's minus 3. And then I have my slope of 1/3. So my change in the y values is positive 1. Y again means up, down. So if I have a positive 1, what direction is that telling us? Do I go up 1, down 1, left 1, right 1 for my change in y of positive 1? Yep, that's going up 1 because y is up, down. So I'm going up 1, and then my change in x is positive 3. So that means I'm going right 3. Okay, so then I go from here, up 1, right 3. I can do it again, up 1, right 3. So I have my second line I can draw, and they intersect right here at that point. What are the coordinates for that point? 3, negative 2. Awesome. Okay, so the solution to this equation, to the system of equation, is 3, negative 2. And we want to write the solution that way as a coordinate point. The x value of 3 and the y value of negative 2 will make this equation true. And if we wanted to, we could check that we're correct by substituting in 3 here for x, 2 for y, and seeing that we get true equations in both cases. All right, we're going to look at one last example of being asked to solve the system of equation by graphing. We have y equals negative 2x plus 2, and then y equals negative 2x minus 2. for this. So let's go ahead and do the exact same thing. So for my first equation, y equals negative 2x plus 2. What is my b? What is my y-intercept for this equation? Positive 2, exactly. So the y-intercept is positive 2. So that is my y-intercept. And then I have a slope of negative 2. So I know that when I have a slope of negative 2, or any integer, I can just put that over 1 to turn it into a fraction form, because any number divided by 1 is itself. Okay, so then I get my change in y is negative 2. That means I'm going down 2, and the change in x is 1, so that means I go right 1. So I can do that. Down 2, right 1, down 2, right 1, down 2, right 1. Do that as many times as I want. And that giving me my first line. And then we can do it all over again with our second equation. Our second linear equation is y equals negative 2x minus 2. So my y-intercept is minus 2, so I'm going to plot this point, 0, negative 2. And then I have the same slope, interesting, the same slope of negative 2. So I already did this. When I have a slope of negative 2, that's the same thing as negative 2 divided by 1. So my change in y is negative 2, going down 2. The change in x is 1, I'm going right 1. So down 2, right 1, down 2, right 1. I can also, this is equivalent to going up 2 and left 1, which we talked about when we learned slope. So I could continue in that direction, and I will get this as my second line. Now it would be slightly easier to tell if I had a ruler when I was doing this, but once I'm looking at this, I should see that my lines do not intersect, right? They're never going to intersect. What do we call those lines when they will never intersect? Perfect, parallel lines. These are parallel lines that are never going to intersect, and I know that because they have the same slope of negative 2. X has the same coefficient, negative 2, but then I have these different y-intercepts, so they're kind of like starting at different places, but they're moving in the same way each time. So they're never going to intersect. There's not a solution to the system of equations. There's no value for x or y that's going to make both equations true at the same time. So we just conclude that there are no solutions to this equation. And the answer is that there are no solutions. All right, awesome everyone.